Good morning. Welcome to the UK FCT Trenchless Tea Break. My name is Nico Mitya. I've also got my colleagues Chris Rogers and Kirill Horoshenko on the line. We're going to talk about a project we're doing called Pipebots, which focuses on micro robots revolutionizing the management of buried pipes. So we go into some details. You have a chance to ask some questions at the end. Please use the question function on the GoTo portal, and I will read them out at the end. Before we start with our presentation, just a reminder of what UK SCT also can do for you. So remember that there are some technical resources available, and you can have some free inquiries to UK SCT if you're interested in any trenchless work, and they will be able to help you. The other thing you see on this slide is also some upcoming events that you might be interested in, but all the information is also on the website. So now let's start the actual talk this morning. So I've already said we're talking about swarms of robots. Important thing on this slide is that there's also a website where you can find a lot more information about the project than we can give you this morning. First of all, I'll give you some background. I assume most of you are familiar with this, but I'll just summarize again what the situation is in the UK. So we know that we have got over 343,000 kilometers of clean water pipes in the ground. We know that around 1,161 million cubic meters per year are lost of drinking water are lost every year due to leaks. We've got over 600,000 kilometers of sewer pipes. And one of the key things is we mostly do 1.5 million roadworks per year related to buried infrastructure. And most of these are trenched rather than trenchless, which is obviously what we're advocating through UK SCT. And one of the key things is the associated traffic disruption costs the economy around £5.5 billion per year, so a staggering amount. But one of the things, even though we know all this, but one of the things we tend to do is that we do pipeline leak and blockage management in a reactive way. So basically that means as soon as we find a leak or an issue, we then go in and assess it. But we don't tend to have lots of sensors attached to our network where we can predict and do proactive asset management rather than reactive asset management. And it's not a surprise, it's really complicated. You see a complicated picture here. This is near New Street in Birmingham, and you can see all the pipes and ducts and other buried assets going back and forth and different pipe materials. One of the key things that's also of interest is that we probably only know around 50% of our buried assets, where exactly they are positioned in the ground. And that has a huge impact, both when we do trenchless activities, as well as when we are trenching to find a buried asset, a pipe, and then try and repair it. So a bit more about the issues and the impact. I've already mentioned that there are lots of street works in the UK. So we spend about £7 billion per annum on utility-related street works. We do occupy the road quite a lot because, as I mentioned, most of this is through trenched activities. And this causes traffic delays. And we know that a large amount of street works are undertaken by utility companies alone. Those are the issues, but if you look at the impacts, we know that it's only 78% of our costs, or the other way around, it's only 22% are direct costs. It's 78% is indirect costs, including social and environmental impacts. So that's delays. That's also issues with where the water goes, where the leakage is. So that is quite a staggering amount that is indirect. We know that we have about 6.16 million days of work in the UK was undertaken in 2014-15. So again, a huge amount. And we have a large amount of road openings. This is some information that was collected by Bob Gallion, former CEO of NJAC, which is now Streetworks UK. But what all this means is that we dig still a lot of holes in the UK, and this incurs unnecessary costs. And there's also a safety issue, because if we don't know exactly where our buried assets are, then there's a risk to health and safety when we dig down, especially obviously with electricity cables, but also with water and gas. And we do know that, again, that there's a lot of discussion, and it's progressed quite a lot, that councils can charge for road occupation, so these permit schemes. And that's not new, and it's been in operation for quite a few years. Different councils are a bit further ahead than others. And again, Bob stated a few years ago that utility companies are delivering the infrastructure that the UK needs to drive up productivity, create economic growth, and deliver government priorities such as broadband and new homes. But as I said, at the same time, they are charged for occupying the roads. So therefore, we have to really work with our councils and try and see whether we can do things slightly differently and do things trenchless, maybe, rather than trenching all the time. But what are the challenges? I've already mentioned a few. So some of the challenges are clearly the accurate location of buried pipes or general buried assets. But also the condition is often unknown, and that means if you're working nearby and you've got an asset that is in a slightly poor condition, because you've got stress relaxation of the ground, there might be some movement, and there might actually be some damage to an asset that you're not actually touching just because of the operation you're doing in the ground. We don't really know exactly what the leakage rates are. Yes, we're using district metering analysis, and there are approaches, but we don't monitor it regularly. There's also potential for ingress of water into pipes. Those tend to be when they are gravity fed and not pressurized, that you've actually got water going into it. And this is sort of your unknown leakage and infiltration rates for sewer system. But one critical thing is that we have really very few permanent sensors that we've attached to our buried assets. We often do go in to a site and then measure it quite accurately at that particular location. But these one-off sensors do have some drawbacks. So have a look at the next few slides. So we've got a few robots that already exist. They tend to be tethered robots, and they've basically got really good cameras on it. You can see different sizes. Interesting enough, I took these pictures at an open day in Hanover, at an Explorer Day it was called, where they were showing this off, and we're actually also showing how they can do jet wash pipes inside. And the activity was that you can actually blow balloons through the pipe doing that. Here's the picture of one of these robots going through the pipe system. There we go, that's just me recording it very briefly. We also know that we use guided wave correlators. So for guided waves or correlators, so basically an acoustic approach where we listen to the leak. So that's used quite a lot. But you do need to have access to the pipe system somewhere, the standpipe or a valve. There's a smart ball system which you can put inside the pipe, and it goes through and takes some measurements. There's also the Sahara system, which is a tethered system that, again, you can put into the pipes. It's an acoustic system. Kirill could tell you a lot more about it, which again tries to listen to deteriorations in the pipe system and also tries to detect leakage. But one of the challenges with all of these existing inspection methods is that they all require human intervention. So you basically have to go to site and place them into the system. They all cause disruption at the surface because you have to block off either a manhole, or you have to block off an area, or even dig a trench to get to the pipe. And they're often quite difficult to operate in complex networks. So it's one thing if you've got a straight pipe, but if you've got complex offshoots, then they're often quite difficult to operate. And this is the sort of environment we find ourselves when we came up with the Pipebots project. And I now pass on to Kirill, who will tell you all about what Pipebots is. Over to you, Kirill.
Thank you, Nicole. Good morning, everybody. What is Pipebots? So the Pipebots is basically a development of microrobots designed to work in underground pipe networks. So you see, I hope you see the animation, which is on the slide. I think it stopped working now by some reason, but basically the idea is to use much higher level of autonomy assigned to robots, which can move independently and collaboratively over a network of pipes, inspecting them pervasively and continuously. This particular simulation shows a real network in a Yorkshire town. It's a clean water network. It's 30 kilometers long, and our simulations combined with real flow data suggest that it will be possible to inspect the whole network like that with around 12 robots within a matter of a month. And we'll repeat this again and again if robots stay long enough alive. So how are we going to achieve this? We have a 5-year long grant from Engineering and Physical Science Research Council, EPSRC. This work started in March 2019 and will continue at least until February 2024, unless we get an extension based on the COVID-19 situation. It involves 4 institutions, the University of Sheffield, who lead it, Birmingham University, Bristol University, and the University of Leeds. We assemble a pretty large team of 40 researchers, and we work with over 30 industry partners who help us to steer this project towards end user needs. Also, we link well to other groups overseas, and I encourage you, if you haven't done so yet, to visit our website, which is at the bottom, pipebots.ac.uk, which have more information and videos as well about our vision. Nicole, would I have a next slide, please? So what we're going to do with this grant? Well, first of all, we feel we need to develop new science for high fidelity in-pipe inspection with autonomous robots. This science is actually beginning to exist now due to Pipebots, but it hasn't been available in the past. So we need to integrate this new science with robotic navigation and communication solutions to work autonomously in large buried infrastructure networks. Nicole mentioned how long network is, so therefore, basically, it's a big asset. And if we were to inspect seriously on a big scale, we need to make sure that we cover a big chunk of it with the autonomy. I mean, also to advance this science from lab prototype to field scales. Universities are pretty good in building something on a desktop, but this time around, we aim to actually roll something out, which can be developed further in terms of TRL and provided as a service or product for the industry. We do engage actively with the end user community for this throughout the research program, and it's not a closed club, so people welcome to join us. And at the end, I'll show a slide how to do so. We aim to establish a world-leading center, research center of autonomous sensing for buried infrastructure, because we are building critical mass as a part of this research, as other people, including our partners from overseas. Alongside the mainstream, the usual research activities, we developed 4 case studies. And these case studies depend to blockages in sewers, leakage in clean water pipes, general asset mapping, which covers clean water network and the wastewater network, and also moving on eventually to condition assessment. Asset mapping is absolutely essential in our view to make sure that we understand where things are in network, and condition assessment absolutely essential to understand what condition this system is in. And this providing us with milestone on the path to pervasive condition monitoring of the pipe networks. These case studies are done in collaboration with our industry partners, and we're always open to new partners to join us on this route. Nicole? Thank you. Where are we now? We are 2 years into this grant. So we are continuing to development testing facilities, which you can see in the top left corner on the slide. we have been making robots, and I'll show you something on the next slide in more detail. We also were doing a considerable amount of work to integrate software to make sure that actually software which goes into robot itself is properly integrated using the robotic operation system, which is commonly used for deploying on robots. Also, a big challenge for us is navigation in pipes. It's a feature scarce environment, and we're spending time to learn how to do that. Also, we testing these robots. So that system which you see on the top left corner actually been used to test the robot, which is in the middle of the, yeah, thank you, Nicole. But also we develop numerical models and simulations to understand how the sensing works in the pipes and how the robots move in the pipes to inform our hardware decisions. Nicole, thank you. This picture shows a blow up of what have been on the previous slide. It is actually a network which we built for one of our sprints, and sprints a short activity which take place to bring everybody in the team together. And particularly sprint 2 was to develop a robot prototype, which I think I'm going to show you on the next slide. On one of the next slides, I guess. Yeah, basically one of those robots which you saw previously actually was tested in this network. So how we organized ourselves? So we got 7 research themes, and these themes, although they look independent, but they are designed to collaborate with each other. Theme 2 is to develop acoustics or ultrasonic-based sensing system capable of measuring properties of the environments inside the pipe. Theme 3 is to build a mobile platform capable of fitting in the sewer and carrying the payload, such as sensors, for example. Theme 4 is to do with a control strategy to make sure that we can get robots from point A to point B, and as a one single node, but also make sure that all the nodes can collaborate together using some reasonable control system which can be deployed on an autonomous robot. Theme 5 is to do with the navigation. As I mentioned before, this environment is feature deprived. GPS wouldn't work underground at all or badly. Therefore, we need to develop a new mode of navigation in pipe using some bespoke system of vision and audio features. And this is the role of Theme 5. Theme 6 is to look at communications in pipe. If the robots are to be deployed on a massive scale, be many nodes, and this robot system need to talk to each other. Otherwise, they just go like a pub crawl altogether, or they just get completely lost and not know what exactly been inspected, what hasn't been inspected. Theme 7, Chris Rogers will tell you more about it, and he also tell you more about Theme 8. But it's to do with the system requirements and function, and also user engagement and implementation. A little bit more about each of the themes. You can see some pictures of fancy simulation on the left-hand side, and these simulations are for how acoustic and ultrasonic sensors work in a pipe. So how they can pick up blockages and how they can listen for leaks, how far they need to get there and to detect something, and how accurate the system need to be, and how robots can collaborate to detect sensors with a high fidelity. So the picture on the right is showing how the sensors are tested inside the pipe. You may spot some of the speakers and ultrasonic sensors on that robot, which we build for 300 mil pipe. Okay, next slide. Thank you. On the left-hand side, you can see actually the robot which we actually built and tested as a part of Sprint 2 exercise. You may see the speaker on the top and ultrasonic kind of style packing sensors on the right, on the left, and the bottom. So there's a camera, there's some infrared lights and so on, so to sense and to control the position of the robot. this robot actually in existence, but the robot, the Death Star on the right-hand side, it is actually impression something we are building now, so which is a fully sealed device, which doesn't have actually moving part on the outside, but actually it can be put in more real environment and operate against the flow or in the presence of flow and other things. So to move up and down, left and right. So this system was designed to cope with realistic pipes. The other thing in theme 3 is to develop software which is intuitive and easy to use, which can control robot. The pictures on the top show how this robot we developed fit in different sizes of pipe. It fits nicely in 300 mil pipe, but just about in 210. And that requires this team to think about miniaturization, to making sure it can fit actually get something in the pipes which is small enough. Also, the modularity of the design combined with the comparison of access panels should make it easy to perform modifications and maintain the field, which is something we look into. Yeah. Okay, next slide. And control theme, we need to get robot from A to B, but also the robot may experience some difficulties of going around obstacles. And there has to be a reliable way to understand actually what's in front of the robot and what the control and actuator system will do to make sure it can move where it has to go. So it is actually a combination of low-level control, high-level control, and also control of a swarm as a whole. So that theme is designed to communicate with theme 3 to make sure that these controls are implemented on real prototypes which we're building together. Okay, next slide. As I mentioned before, navigation is a big issue. So if robot doesn't know where it is and where it has to go, it'll be quite challenging for the autonomy to be working independently from human being. So therefore, the navigation theme looking at, first of all, mapping of the whole system or big chunk of it. And you can see on the left-hand side is actual digitization of a image taken in real silver with real camera, and also the representation of that using a simulated map based on real data. And on the right-hand side, you can see actually simulation based on actually anticipating where all but needs to go and understanding what uncertainties are depending on the algorithm for the navigation it uses. So to summarize, this theme actually designed to map and to localize the devices when they operate independently in the field. Theme 6, communication. Our simulation suggests if robot has no communication, so it's in danger of either just grouping up together and going like a big group on a pub crawl, so or it's just getting completely out of order because it wouldn't know where prioritize its movement to. So therefore, theme 6 look at how to send messages from robot to robot, how to get messages from above ground to actually instruct robot to do things, and how to send data back above ground to make sure that operators know where the robot's been and what data they collected. And also the data on the status. It's quite a challenge because radio waves don't go very well underground, particularly in clean water pipes, which are pressurized and filled with water. Acoustic waves go better in clean water pipes, but also there are some issues in terms of the pioneering research to overcome. And that's the purpose of this theme. I think I'm passing you on to Professor Chris Rogers now. So from this point on, thank you.
Yep, you are. Hi. So Chris Rogers, some of you may know me because I've been working broadly in the field of and on behalf of trenchless technology, golly, for very many years now. What I want to do is just take what have been a very serious, serious set of challenges, technical challenges that you've just been introduced to, into the wider sphere of why we're doing it and why we should advance this as a way of addressing the issues of our buried pipelines. And of course, what we should be doing is starting with people. So right on the top left-hand side, we talk about public health. And that is why we have clean water pipes, we have sanitation. It is effectively to support people and society and in effect underpin civilized life. So we have that translated into action, obviously via water companies, who then are responsible for responding to environmental and social pressures. The social pressures, of course, being the fact that they are dealing with the end user. And so we have now a responsibility to think about this valuable resource that we put enormous amounts of energy into to create clean water and then take dirty water and return it to the environment. So we have to marshal that resource responsibly, and we have to do it in such a way that it meets then certain quality requirements, quite naturally, but we also have a responsibility to engineer our systems for the benefit of, well, society and individuals and the economy that sits all around it. So we need to bring in these dimensions. So what I want to now focus on is how we are linking our research through from academia through to industry, and how industry is then helping to shape our research. It's co-created, and necessarily so, so that what we're doing is relevant, but also what we're doing, and that allows us to stretch industry thinking. So we're not looking at being constrained by, but at being informed by industry needs. And that dynamic is the really inspiring underpinning activity that goes on in this type of research, where we have, rather than a very strict program of research defined from day one that we then carry through, what we have is funding for 5 years to take the research into the most appropriate spheres in order to deliver on the ultimate outcome. And so we have a real opportunity here to carry out some scientific and engineering research that will take us into new fields. But ultimately, then we need to build the case for change to adopt this research. And we need to make sure the research aligns with the current and potential future regulations, codes, standards, legislation, taxation, all of these other things that we need to work to. On behalf of the society that we're serving. So what I want to talk about then briefly is how we create the business case for change, or the case for change, the alternative business models that will allow that change to happen, because it will demonstrate what the investment is and what the positive outcomes will be, and then to look at governance frameworks. So this all prepares the way for what we call the industry transformation, from being reactive, for example, to failures, to leaks, to being proactive, and that is carrying out action to avoid the this idea of failure. So Nicole, could you pass me to the next slide? What you've now seen is one way in which we've been able to advance our work. We have talked about different themes, but we've also talked about this being a seamless integration of the activities. And so we're looking now across the whole team to be influenced by every other discipline, every other lens that we're bringing to this problem, so that we then create genuine collaborations. And in a technical sense, I would talk about the move towards transdisciplinarity, where we work beyond our disciplines, and that's working really quite well. Now we can do that via meetings. But one extremely powerful way of doing that is via what we call sprints. And these sprints then take a particular challenge, a subset of where we wish to go to, but bring the whole team together to work on this challenge for a specific period of time, so let's say a month. And what we've learned then from the second sprint, and you've seen some of the technical outputs and the robots, is that, well, although we can do things successfully within our themes, bringing them across in terms of hardware and software integration is a work in progress, quite naturally. That's not unsurprising given where we are. Managing the software is also a challenge, and that's something that we're now taking to heart with the next in the process of program rather of our sprints. And then we had issues around the system architecture. Was it well enough defined from a systemic perspective, and so on. And it was also interesting to look at how ambitious we started with our sprints, and then realized that, in fact, in order to get to where we needed to go, we needed to be more stepwise in our approach so that we could achieve various things. So there are all sorts of high-level outcomes. But then to move to the next slide with the research challenges, not surprisingly, we want to go smaller. And so, having learned from the big, then we know where we want to go, and there are challenges associated with that. Likewise, challenges for better locomotion. In-pipe computer vision is an issue, of course, particularly given the environments that we've got. So we need to address these technical challenges. So we've learned things around sprints. We've learned things around how we deal with our specific focuses of research, and that then feeds back into the themes. And so there is this dynamic interaction between collaborative advancement and individual advancement. And this is taking us to where we need to go. So, Nicole, if you'd move on, please. If we now take this wider view, then what we're looking to deliver is a range of benefits to a range of beneficiaries, and we list three here. Utility companies, quite obviously, and their subcontractors will then be able to autonomously monitor their pipelines in a way that we've not been able to do this before. So pervasive sensing, swarms of miniature robots going into pipelines, allowing us to move all the way through the pipelines to assess their condition would be an enormous advantage. And what it will allow us to do is to act in advance of failure rather than respond to failure. So we might well be able to pick up leakage with our robots, but if we can identify the points that are vulnerable so that we can then use, for example, in a planned way, our various techniques to maintain and upgrade pipelines, then that would open the door to trenchless technologies far more than having to respond to something that has failed, for example. And so this whole idea of enabling trenchless works to be carried out sits at the heart of what we're effectively doing. We can look at instrument manufacturers, and of course, by advancing the science and engineering in our individual spheres, then we're looking at creating new ways of doing things. And so there will be benefits to that group of stakeholders. And then we take a wider view from society and individuals, so the general public. Because, of course, what we will do is look at manifestly reducing the number of failures and therefore the interruption to services, providing a more guaranteed supply, if you wish, no interruptions. Then we come on to this idea of, well, the fewer road closures, less traffic disruption, particularly if we can move to trenchless operations as the routine reaction to the condition assessments that we can carry out. But effectively, that list there only starts to scratch the surface. So if we go to the next slide, this isn't specific to Pipebots. This is specific to any intervention in a system of systems. And so what we've developed is a suite of methodologies over the last 20 or so years of research, much to do with cities and urban systems, but it can be applied to any intervention in a system of systems. And that intervention could be Pipebots, or it could be Trenchless technology, or it could be, well, whatever. And so in order for we're going to change the way things are done now, we have to, first of all, compile a rigorous evidence base. If you click on. The second then is to draw on that evidence base to make the case for change. And the case for change needs to be comprehensive, but it needs to be understandable. So it needs to be accessible and transparent. So all of those who need to understand it can understand it. But even if you have a wholly compelling case for change, that's not enough to bring change around, because you need the business models, what I will call the alternative business models that would implement change. What I'm talking about here, though, is not just the pound note elements of business models, but looking at balancing all the multiple forms of value against all the costs associated with it. But this idea of value and cost is really looking at all the positive outcomes of a system intervention balanced against all the negative outcomes of a system intervention, one of which might be an investment is needed. But even if you have the business models and they're compelling, it doesn't mean to say they're going to work, because what we then need to do is look at all of the forms of governance that sit around it to enable the business models to function. We have the formal systems of governance, the legislation, regulation, taxation, codes and standards, those things that we need to address to look after the interests of the end user base and the interest of the environment and so on. But then we have the informal systems of governance. So individual and societal attitudes and therefore behaviors, societal norms, practice norms. And practice norms is a big one here because the water industry has always done things in a certain way. And what we're now doing is challenging that way. And a lot of people have been promoted to roles in which they're very good at the existing way of doing things. And now we're thinking of doing something radically differently. So if you click on, you will see reflect and iterate. And of course, this is what engineers do. I mean, the root of the word engineering is ingenuity. So we apply ingenuity to solve problems or address issues. And what we do is we iterate around the problem and the solution space to come out with a most appropriate set of potential outcomes, options to be taken forward. So that provides the core of the research element that I'm bringing to this. If we click on again, here is an example, and this is to do with something quite different. It's to do with a green infrastructure corridor, where I looked at the system of interest, that's the green corridor, and looked at how it impacts on all of the other infrastructure and urban systems with which it might interact. And I get this great long list, and in fact, it's bigger than is even seen on the screen. And at every point of interaction, there's a dependence or interdependence, which is somewhere where you might be able to raise value. Certainly there would be a potential impact, and that could be positive or negative. But if you then look at how you enhance all of the positive impacts in the other systems and reduce or remove the negative, then the business models start to become stronger and stronger. And this is where we're going with Pipebots, because what we'll then be able to do is look at how it interacts on all of those other systems and bring in business models that will address the issues of, for example, the health and well-being of people in cities, because we've got fewer trenches. There will be less noise, there'll be less vibration, there'll be less particulate pollution, air pollution, there will be fewer delays to traffic, and so on and so on. And so we've been talking about the social costs and the indirect costs for many years in the trenchless industry. Now we have a means of being comprehensive in the way we look at the impacts and therefore the business models. So if you go on, Nicole. So where do we go from here? Well, clearly we're looking at pure science and engineering to get to where we need to go, and we will take this to higher TRL levels, as we call them, to introduce them better to industrial application, working with and making sure it's adopted by the water utilities as we go, developing a new governance framework so that it can be put into practice without governance regimes getting in the way, regulation in particular. And then looking at delivering this transformative vision for going from reactive to proactive in the water industry. And that's the thing that will lead us to avoid the disruption of trenches in streets, or to put it another way, enable the trenchless technologies to then become part of a solution that limits the adverse impacts on individuals, on society, on the economy, and on the environment. If you click on. So that gives you some indication of just how we're looking to change the world. It is a big ambition. If I talk in the olden days, I might have talked to people in the pub about, well, we've got this idea of swarms of miniature robots, and immediately you talk about that big ambition. It captures the intention. Well, we're now looking at making this type of thing a reality, but then bringing far wider sets of benefits than you might expect than if we were just creating miniature robots. So thank you very much for listening, and you can see how you can contact us here, and we do wish to collaborate. It is very much an open collaboration that we're involved with, because it's funded by the Engineering and Physical Sciences Research Council on behalf of the government. And I think we're now open for questions.
Yeah, thank you, Chris and Carol. I have one last slide for UKSCT for the upcoming events. We've had a few questions coming in. The first one that I read out is about the ambition of the last 20 years. And the question is, would you like to access the current industry best practice? And how close are you involving commercial partners? Maybe Carol and Chris can answer that one at the time. Carol first. Not sure if we lost.
Sorry, it took me a while, but I'm on mute. Thank you so much for your question. It's a good point. We have a pretty active steering committee, which mainly consists of industrialists. Also, twice a year, we run a specialized workshops or webinars now, so which are attended by the industry, including those who potentially can develop this technology as a product or service. So this is usually attended by anything between 30 and 50 individuals. So we do listen to their advice, and we take the advice very seriously. But we always open to new collaborations. Anybody who would like to help us to develop this technology towards a higher TRL? Because the universities, I mentioned in my presentation, normally develop something with TRL 3, 4, 5, and then somebody else needs to take it higher up to make sure it's not lost in papers, dusted on the shelf. Chris, do you want to add something to that?
Yes, absolutely. Well, I talked about this work having been co-created with industry, and it was. And so we will start with a group of project partners. And project partners have a particular meaning as far as the research councils are involved. And that is that they are organizations with whom we will have co-created and with whom we will work, because they will be contributing in kind to the work to help us advance it. And we have a very impressive group of project partners to start with. But what I would always say is that it is the initial cohort, and we would then look to grow our project partners as the work progresses. When I ran the programs called Mapping the Underworld and Assessing the Underworld, we started off with a very respectable set of project partners, but we increased the number by a factor of 3 or 4 by the time those programs matured, with others getting interested in what we were doing and then wishing to take part. So we would be very interested to hear from you if you wish to engage with us.
Yeah, and I think I just want to add also, as Chris said, we're trying to come up with an evidence base. So clearly we would like to have access to current industry best practice, because we want to benchmark what we are doing against what's done at the moment and what is the best practice, how things are done currently. So yes, hopefully you've got the contact details, so contact us and we'll be open and more than interested to collaborate.
We're welcome to share our position paper with those who are interested to do so, to read it. That's what we produced in the first year of this grant. And this probably needs to be updated because something been happening between now and then.
Next question, probably directed at Kirill, is at what TRL do you consider the bots to be at present?
Probably somewhere between TRL 2 and 3. It's the problem we face, nothing like this exists right now. So most of a majority of those solutions which have been developed, they're not autonomous. They have a tether. So we developed something which is brand new. So therefore, we're looking at a quite low TRL level now. But we do work closely, like we mentioned a few minutes ago, we do work closely with key water companies. And we do consider putting bids, particularly to Off-Water Innovation Fund and similar funds available to upscale the TRL. So in collaboration with water companies, and those companies can deliver the solution at a high TRL level.
Thank you. The next question may be also a technical question, so probably also to Kirill. For potable water, how can the pipebots navigate along pressurized mains against flow, and how are they retrieved?
Well, that's an issue which we yet to be resolved. So we started with the sewer pipes because we consider sewer pipes more practical for us to address the challenges faced. So what we're going to do, we're likely to move on into clean water pipes together with our collaborators in Holland, KWR, who are actually developing solutions for that purpose. So specifically for pressurized water pipes. The challenges be not completely dissimilar to the sewer pipes in terms of the localization, albeit they probably be using more acoustical information to understand where they are. But the challenges of inserting and getting back these robots will be considerably more difficult. I don't know if you answer your question.
Probably, otherwise probably have to follow that with another question, but it goes along the similar lines or so. The next question is, what's the minimal pipe diameter in which pipebot can get in? Is it 100 millimeters? Question mark.
Well, the prototype we developed now is going in 300 millimeter pipe. We're working actively on miniaturization with a view we may get down to pipes which are 50, 75 millimeter diameter with a smaller pot. So it presents considerable challenge, particularly in terms of the actuators, which can find off the shelf. But we don't have a very clean answer right now. So how small the bore will be. Some companies like Synthetech, who produced robots for gas pipes, they managed to develop something similar to go into pipes which are 50 mil and above. We probably should aim for something similar like that.
Thank you, Kirill. The next question is, does the remit of the pipebots research also include the mapping of their host pipes?
I think that'll be, in my personal view, that'll be a really good start for getting robots into the pipe. It will be really difficult to do something sensible without a map. So the first robots which go in will be probably inspecting, not so much inspecting the pipe, but taking very careful maps of the system. And this map then inform the way the inspection robots actually work. Don't know anybody, Nicole, Chris, you want to say something to it?
Yeah, yes. So I'll just pick up on that. So yes, the answer is yes, because we will have the ability to map the system. That would be one of the prime advantages of this particular technological advancement. And the truth with all of these pieces of work is that we are advancing them in parallel, so that we can then take the localization and the mapping work through to a point where we could use that as a deliverable, and we could then scale that up. If we're now looking at miniaturization, of course, then where we started with is, well, there's a pipebot that's that big, and we could then bring it down to be very small indeed, and it would have all of the sensors on, wouldn't it? But of course, then the answer is, well, it doesn't need to. What we might end up with is a series of pipebots, all of which do different things. So we might have a mapping pipebot, we might have an acoustic sensing pipebot, and so on. And then these would need to talk together. So it's a different way of approaching it. And it could be that the pipebots would physically join at some point, or it may be that they could all work autonomously. So just the idea of a pipebot as being a single all singing and dancing device is not necessarily the way that we would develop. But of course, we're free to develop in whichever way is most appropriate to get to our target of smaller pipes with multiple functions.
Chris, you might want to take the next one as well, although Kirill can add. Are there any international aspects to this research, i.e. checking, liaising, collaborating with other non-UK water companies, or an appetite to offer this solution to beyond the UK at some point?
Yes. Okay, you want me to add to that? But of course it is. I mean, and the reason why this was funded is not because it would satisfy a UK need, it's satisfying a general need. And so yes, we do have international contacts that we are with which we're working to bring this into play. And we all have our own different specific sets of challenges or contexts to work in. So in some cases, in North America, they deal with bigger pipes. And what they might be really interested in is something of the size we've already got, because immediately it could deal with a greater proportion of the pipelines that they have there than we have in the UK. So what we would say is we're looking at creating a device that will serve our purposes, but then looking at how it can be applied in other contexts. And so for pipelines, well, we're looking at water and sewer, but pipelines come in other different shades of utility function. And basically they're cylinders, but does it need to be a cylinder in which this pipebot then works? And one of our colleagues at Leeds has been doing work with robots that have gone into pyramids to look at the inside of pyramids. Well, I'm not sure that we need to know the condition of the inside of pyramids, but but there are certain things we need to know about them. Anyway, so yes, the applications could be far broader.
Yeah, and within Theme 8 also, we're already planning some international trials as well. So to utilize international facilities to trial our prototype robots. So it's definitely on the agenda. Kirill, did you want to...
We do have strong links with Europe, Australia, Hong Kong, and United States. In particular, United States, Dan Murray, who is a senior figure in US EPA, is on now a steering committee. So it's a good point you make, but we do take this into consideration when we develop our links.
Another question is, do you have any plans for gas pipes?
Yes, gas pipes is obvious next step. We have a few people on our steering committee, particularly Synthetech, so have a very good track record in developing robotics for gas pipes. Also ULC, and it's not something we actually are focusing right now, but we have people actually on our steering committee and as a partners who can roll out the technology for specifically using in the gas pipes.
those are all the questions that have come up so far. We have had an offer to work with someone who's recovered pressurized water pipe bots from water mains. So we can get in touch with Nick. I've got the email, so I'll pass that on. Are there any more questions that the audience might have?
Maybe one point I can make as well. So pipe infrastructure is quite a conservative, pretty much obsolete system very often. So in order to get the robots in, so one thing it may need to change to become robot friendly. So things which already exist in these pipes, including say acoustic leak detectors and other things which may serve as a hub or potential beacons to understand better where these robots are in the system, may be quite useful. But in the future, it may need to develop to help robots to get in and get data in and out and stay localized.
Thank you, Carol.
So could I just add? There is another dimension to all of this research that we're carrying out. You saw a picture of some pipelines sitting on a test bed area. There are two very specific new facilities that have been funded by the government through the Engineering and Physical Sciences Research Council under the umbrella of UCRIC. UCRIC is the UK Collaboratorium for Research on Infrastructure and Cities, and it has been invested in to the tune of £138 million by the government. That's a matched investment with industry and universities then providing the matching funding. So we're getting on for £300 million worth of new facilities around the country for doing research on infrastructure and cities. There are 11 new laboratories. The new laboratory at Birmingham is the National Buried Infrastructure Facility. It's worth £28 million, and so it's a very big investment and a very big facility, and it includes a pit for doing everything subsurface, soil structure interaction, pipelines, tunnels, and so on. The pit itself is 25 meters long, 10 meters wide, and 5 meters deep. So it's a very significant test area with a whole raft of other facilities that sit alongside it. At Sheffield, we have the iCare facility, which does all things pipeline. So it's a water facility, and therefore we can do all sorts of clever things with water. And if you go into the iCare facility, you can see any number of pumps and valves, and they can put pipelines into the ground and then look at their functionality. And if you then look around the rest of the country, we have other facilities as part of UCRIC. So we now have this ability to do research at a scale that we've never been able to do before. And UCRIC sits above our work and other work in pipelines, in construction techniques. And underpinning all of that activity is this suite of methodologies that I spoke about, which I'm now building into a theory of change for how we make the case for doing things very differently in support of the end users, the individuals in society that ultimately pays for our services, in support of the economy and those who fund the activity that goes on in the various pipelines, and the environment, and the looking at how we protect our resources and how we ensure that we don't adversely affect the environment as we carry out our engineering work. So there's a much bigger picture to the work that we're carrying out, and again, we would be delighted to introduce you to that.
Thank you, Chris. That was really good. We've had one last minute question come in on Pipebots, so I'll read that out, and that's probably the final question as we're on the hour now, 12 o'clock. So it is, how do your robots access the linear pipe run network? This will be key for moving technology into clean water and gas systems where 90-degree stabbings with smaller diameter than main are the norm. Any ideas, Carol?
Yeah, there's been some work on chambers to get things like smart ball and other systems which are tethered, unlike smart ball, into pressurized pipes, both gas and clean water. Syntatech I mentioned already, so they have very good technology for getting this into pressurized gas pipes up to 70 bar. So therefore there is technology, and we're also working with the Wessex Water and other water companies to get this technology into rising mains, which are also pressurized. So yeah, it requires a bit of technological developments further, but it's not insurmountable.
Thank you very much. And I would like to thank the audience for listening. I hope you enjoyed the presentation. You've got contact details to contact us as and when you like. So please do engage. As we've all said, we're more than happy to engage with all of you and to find out what best practice is and to also demonstrate our progress. So please do keep in touch. I believe when Lynn closes it or Alice closes the session, it'll close for all of us. So thanks from the three of us for listening, and wish you a good rest of the day and rest of the week. Thank you very much. Bye.
Sure.